All right, so I want to do a video on rational functions. They use rational functions a lot of times when we're looking at limits, and I think it just would help you if you had a little exposure to that now. Okay, so rational functions are functions that look like this. Okay, so there's a polynomial on top and a polynomial on the bottom. So the numerator and the denominator are both polynomials. My pen, I dropped it, so the pen doesn't quite work as well as it used to. Okay. All right, now we're gonna, in this section, I'm looking at wanting you to see the connection between domain and then whether you have wholes or vertical asymptotes. The domain of the function kind of goes with wholes or vertical asymptotes is the way to think about it. So, and both of those have to do with you can't divide by 0. So you can't have a 0 in the denominator. Okay. Division by 0, that's undefined, right? So the domain is the set of all x's, any number you can possibly think of for x, except for those making the denominator 0. At each x where the function is undefined, you're going to have either a whole or you're going to have this vertical asymptote. Okay. All right. So okay, so if you can completely cancel out the common factor associated with the number. So you're going to either have a whole or a vertical asymptote. If you can completely cancel out a common factor from the top and bottom, then that gives you a whole. And the x-coordinate of the point is equal to the number you would get from that common factor. And then you can plug that in to get the y-coordinate. We're going to do an example in another set at another time. And then if you cannot completely cancel out the factor associated with, if there's not a common factor and you can't completely cancel out the factor associated with the number where it's undefined, you have a vertical asymptote with the equation being x equals to whatever that number is. So the number I'm talking about is at each x where the function is undefined, you're going to have either a whole or a vertical asymptote. Okay. If you can completely cancel out the factor associated with whatever that undefined, that x is, if you can cancel out the factor, then you have just a whole. Okay. If you can't, then you have actually a vertical asymptote, which is a bigger problem. Vertical asymptotes cannot be crossed by the graph. Okay, you could have a bunch of wholes and a bunch of vertical asymptotes, or you might not have any wholes or vertical asymptotes. Wholes are kind of minor problems. This is not a really technical term. It's like they're fixable problems. Okay, they're kind of minor compared to vertical asymptotes. Vertical asymptotes really cause a lot of problems. So like a whole would be like if you had something where the function's just not defined at that one spot. So we can just come in here and plug it if we needed to. Okay, but if you have a vertical asymptote, that's when things like this happen. You have a graph and it'll look something like that. And then right here, you might have this vertical asymptote. Can't really fix it. You know, here the function's going up that way. Here it's going down this way. It's really not a way to just plug the hole. See, it's not a minor problem. It's a major issue. Major problem. Okay. All right, so I'm just going to over to the side here give you kind of an example. So like if you had, say, x minus 1, x plus 3 on the bottom. then your function is undefined at both of those spots, okay? But if on top you had, say a 3x with the x minus 1 like that, then in reality, you just have a hole. You just have a hole here, because see how the x minus 1 factor could be canceled out? That's like plugging the hole. So the function would be undefined at both 1 and -3. But because you can cancel out the factor associated with the number 1, then you have a hole at x equal 1. Okay, you have a vertical asymptote at x equals -3. Okay, so that's just kind of a quick example showing you what I'm talking about. So like that original rational function right there, it would have simplified to be 3x over x plus 3. So you could get rid of the hole in a way. It's like you're just plugging it, okay? But the x plus 3 you're stuck with. So you're going to have a vertical asymptote there. All right, now let me move on. All right, so let's talk about x and y-intercepts. All right, so with x and y-intercepts, this is just like with any function. So to find an x-intercept, you look for, you plug in, you let y equal 0. Okay. And then for a fraction to be 0, remember that the numerator must be 0, but not the denominator. So you have to watch out for that. Okay. You can have more than one x-intercept. You can have bunches of those. Okay. Now, y-intercepts are found by letting x equal 0. You cannot have more than one y-intercept since you are dealing with a function. Okay. So like if 0 went to more than one thing, 2 different numbers, that would not be a function. So that's not going to happen because you're dealing with functions. Okay. But it's okay if if you had a rational function that maybe did something like this. Well, let me just give you an easy example. Like a polynomial, for instance, looks something like that. You can have lots of x-intercepts, and it's still a function. Okay. All right, so let's move down. Now, this is really important when you're dealing with limits. Okay, so, there's a point at which we're going to talk about limits at infinity, okay, and then limits that wind up having an answer of infinity. Like we're going to look at limits, what happens when x goes to infinity or negative infinity, and then we're also going to look at limits where the function approaches infinity. All right, so these at vertical asymptotes, you're going to have a function that goes to infinity or that goes to negative infinity. That's going to happen a lot. So those are like infinite limits. All right, what we're talking about in this section is the horizontal, slant, or they can be really other curves, asymptotes. Those are associated with end behavior. So like the domain and vertical asymptotes are basically the same concept. Well, the end behavior of a function kind of goes with the horizontal or slant asymptotes. And when we get into the limit discussion, the horizontal asymptotes, excuse me, the horizontal or the slant asymptotes, the asymptote associated with the end behavior, that tells you the limit at infinity, not infinite limits. Okay, I know it sounds strange, but it'll make more sense later. All right, so these other asymptotes, not the vertical ones, but the ones like the horizontal, or they call them sometimes oblique, means slant, really have to do with the end behavior of a function. What does it do ultimately? what does the function eventually do if you let the x keep getting bigger and bigger and bigger? So there will be at most one of these. These can be crossed. Okay, vertical asymptotes cannot, but eventually the graph stops crossing and keeps getting closer and closer to it. So sometimes you'll have like a horizontal asymptote. The function will do something like this, but then it'll come back and get closer and closer and closer to some horizontal asymptote. So it might cross it in the short run, but then eventually it starts just getting arbitrarily close to it. Okay. All right, the end behavior or the non-vertical asymptote of a rational function can be determined by using division to rewrite the expression as a mixed number. Now, you might not have a lot of experience with division. Chances are you're not going to have to do this very much. But if you can take your rational function and write it in this form, I think of it as a mixed number, then it turns out that this right here helps you to determine your non-vertical asymptote. The non-vertical asymptote turns out to be y equals whatever that quotient turns out to be. Okay, so sometimes that quotient turns out to be y equals 0. Sometimes it turns out to be y equals some number other than 0. Sometimes it turns out to be something linear, like y equals 2x plus 1, but it really can turn out to be any curve. It's just we normally don't deal with the ones where you get something that's a curve and not just a line. Okay, so what this means here is when x gets really big, okay, when you let x's get really big in the positive direction or really big in the negative direction, then if you have any terms where you have x's in the denominator, they'll be virtually 0. Okay, so think about that. So if you have like a 1 over x, and you start with 1 over 1, but then if you let that x get bigger and bigger, and you keep plugging bigger and bigger things in, do you see how, well, here it was a 1, here it's only a 10th, here it's 100th, 1,000th, 10,000th. It's getting tiny. It's approaching, this is really approaching 0 ultimately. Okay. Okay, so the non-vertical asymptote, we just kind of talked about this, really turns out to be y equal this quotient. If you can get it into that divided form, and it may be the x-axis, which is y equals 0, some other horizontal line, which is like y equals 3, or a slanted line, like y equals 2x plus 1. But it really could be even some other curve. We just normally don't deal with those. Okay. All right, so you're going to have a horizontal asymptote. You're going to have y equals 0 being the asymptote. Okay, it's basically the x-axis when the degree on top is smaller than, I'll say less than, it's more appropriate, is less than the degree on the bottom. So if you have like y equals x over x squared plus 1, the degree on top is smaller than the degree on the bottom. If you let x's get bigger and bigger and bigger in there, the denominator gets huge much faster than the numerator, then this is going to have an end behavior of y equals 0. And it turns out that's going to help you if you were asked to figure out the limit as x approaches positive infinity. Okay. All right, now you're going to have a horizontal asymptote that's not the x-axis when the degree on the top is the same as the degree on the bottom. When the degrees are equal, I'll write it that way, is equal to, degree on top is the same as, is equal to the degree on the bottom. The equation will be y equals some number other than 0. Okay, so like if your function was y equals x squared, 3x squared, let's say, plus 5, down here we had equals x squared minus 1 or plus 1, then x squareds being the same like that, the degree of the top and the bottom is 2. Okay, degree's the same. And so you're going to wind up having a horizontal asymptote at y equals 3. You can do division, okay, but it's not always the easiest thing. You actually could just take the coefficients of the leading terms on the top and bottom, and that would give you the same thing. So 3 over 1 would be your asymptote on that one. Okay, now, all right, the last part has to do with when you wind up getting a line that's not horizontal as your other asymptote, when the end behavior is like a slanted line, sometimes called an oblique line, something like y equals 3x plus 2 or 2x plus 1. All right, this occurs when the degree on top is 1 more than the degree on the bottom. Then division could be used to determine those, and the equation would turn out to be something in the form y equals mx plus b. So like if you had on top, say 3x squared plus 5, but down here you had, say, x minus 1. If you did division, the degree on top being 1 more, you would wind up having something x left, and then maybe plus a b. But if it's 1 more on top than the degree on the bottom, then you're going to have something like that. Now, it's interesting to note, if the degree on top is 2 more than the degree on the bottom, the graph will approach a parabola. Its end behavior will be a parabola. So it'll look like a parabola in the long run. And that's another way to say it, by the way. End behavior of a function is kind of what it would look like in the long run. Like, what does it look like eventually? Okay. If the degree on top is 2 more than the degree on the bottom, the graph will approach a cubic function. Gosh, my pen is not working. It will be a cubic function. We just typically don't deal with those. Okay. All right, so that's that part. All right, so the horizontal asymptotes, the asymptotes that are not vertical, they could be horizontal or slanted, those actually help when you're asked to talk about the limits at infinity as you pick bigger and bigger x's that go in the positive direction or the negative direction. What does your function approach? That helps you answer the question, what's the limit at infinity? Okay, so I'm going to add that to that. This is something I like to use in my pre-calculus, but I just want to add that horizontal or slant asymptotes have to do with what the function looks like in the long run. This deals with limits at infinity. So like a typical, here's a common rational function. Okay, but if you only look at it in the long run, okay, basically this is going to look like a horizontal line. See, this will keep going in the long run. This will keep going, getting closer and closer and closer in the long run. So if you close out all of that and you just look at it far enough away, you get rid of all that, you look at it far enough away, it's just going to look like the line y equals 0. That would be the horizontal asymptote for that. And then 0 would be the limit as x approaches positive infinity and as x approaches negative. Okay. And then what we're saying is sometimes you don't have a horizontal line y equals 0. You might have y equals 3 or 5. And then you sometimes don't even have a horizontal line. Sometimes you have a line that's slanted, or you even have like parabolas or cubic functions. Rational functions are super cool. We just wind up not being able to spend the time we need to in pre-calculus, but they wind up being really important for the discussion on limits.